Good morning, everyone. I'm not sure if you guys can hear me and can see my screen. Yeah.
Yes, we can, thanks.
Yeah. Okay. My name is Sandile, and I'm being supervised by Prof Mwangi and Prof Quant. Today's talk is going to be titled Plasmonics and Magneto Plasmonics as Approaches to Enhance Photoconversion Efficiency of PV Devices. Okay. So my outline, first I'm going to talk about the device fabrication, and I'm going to give motivation for the magnetic nanoparticles as compared to the traditional plasmonic particles such as your noble metals as gold and silver. And I'm going to look at some optical simulation and experimental results. And I'm going to conclude and I'm going to explain and I'm going to talk about the future work that we're planning to do. Okay, so firstly, there's two ideas that that we were planning to do to fabricate. So the first one was a PN junction and a PIN junction, and these are the layers that we're supposed to fabricate. So the P layer was supposed to be 20 nanometers, and gonna make a P type by using by embedding aluminum ions, and the intrinsic layer was supposed to be is 300 nanometers, and the end layer is 20 nanometers. Okay, so first device that we fabricated was a simple PN junction. So here what we had a 300 micron wafer, and then we embedded we implanted P ions at an NH of 20 keV with the fluence of this. And with this, and these are the parameters that we got an efficiency of about 0.291% as our power conversion efficiency. Okay. Yeah. So why Magneto Plasmonics? So light absorption losses in noble metals are usually lower in ferromagnetic metals, which results in stronger plasmon resonances and larger enhancement of magneto-optical activity in magnetic structures. So the combination, so we propose that the combination of plasmon and magnetic nanoparticles could lead to higher absorption. So magnetic nanoparticles haven't been applied to silicon-based PV devices. So usually first, before I go to the lab, I usually do calculations in order to see, in order to look at the theory and produce some of the so that I should know with what parameters or what size of nanoparticles I should produce in the lab. So first, I'm going to look at their scattering and their absorption cross sections, and I'll look at the ion nanoparticles as their extinction cross section, which is just the sum of scattering and absorption. So here, looking at my calculations, we look at nanoparticles as little as 2 nanometers to 70 nanometers. So as you can see here, mostly scattering usually. We see some scattering starting to dominate at around 30 nanometers. So now I know that when I go to the lab, basically my nanoparticles, I should keep them around I should try to produce nanoparticles as the size of 2 to about 20 nanometers. Okay. So these these nanoparticles, they usually exhibit they're usually referred to as superparamagnetic nanoparticles, as the particles behave as if they have a net magnetic moment, but do not possess a permanent magnetic dipole. So the motivation for incorporating the magneto plasmonic nanoparticle is that previous plasmon enhanced photovoltaic devices were based on interaction of free and bound electrons with an applied electric field. With an applied electric field, But interactions with the magnetic field, that means the B component, of an incoming electromagnetic wave were not considered. So as I've said, we propose that the use of magnetoplasmonic particles should lead to the enhancement and tuning of the absorption of sunlight to match the band gap of the photoactive layer. Okay. So one of the things, one of the softwares that I've used to simulate the magnetic nanoparticles is this. So what it does is that it simulates the nanostructures, magnetic nanostructures, which are these super paramagnetic ones, by studying the atomistic simulation following the Monte Carlo and the Landau-Lifshitz Gilbert approaches. So in this method, in order to determine the first magnetic property that we have that we want to determine is the Curie temperature, which is defined as the temperature where this magnetic material starts to lose some of its magnetic properties. So that here we have we make 3 approximations. In order to get it, we look at we fit it using the Curie block, and then we use the Kurzma incline, and then we use the derivative of the polynomial fitting. Yeah. So here, when you look at the properties of the magnetic nanoparticles, first we look at the magnetization, and we see that starting from the 4 nanometer to the 10 nanometer spherical nanoparticles, we see that as the size increases, that means that also the Curie temperature increases as well. So now, when you look at so now when we change the shape of the nanoparticles, so compared to plasmonic nanoparticles, which usually depends on the shape and size. So now when you look at the shape of this magnetic nanoparticle, when you change it and make it a block or make some sort of an octagon, because when we know that most plasmonics, they depend on the shape. If it has a lot of sharp edges or a lot of corners, you know that light gets scattered and you get the different places. But here, when you change that, that means it doesn't really have any effect, but we see that the Curie temperature is most likely the same, even when we change the shape of the nanoparticle. Okay. Now, when you look at the causal nanostructures of these magnetic nanoparticles, so first we look at the 4 nanometer particle, and we play with the ratio of this nanoparticles. So we have pure iron, and inside, which is a core, we use nickel. So we see that when we put nickel, when we increase the ratio of the 2 now, as we're increasing increasing the core, we see that the Curie temperature decreases as it's trying to get back to the original Curie temperature of nickel. And when you also increase the size of the nanoparticle, making it 8, this trend is we also see the same trend here. Even when we change this, the size of these magnetic causal nanoparticles, we kind of see that the trend is also the same, that the Curie temperature decreases as we increase the size of the core. Yeah.
You've got 5 minutes.
Okay. Yes. This trend is also we see it even when we try to put the iron at the corners. Yeah. Okay. Yeah. Even when we reverse the chemical ordering, we still get the same thing here. Okay. So now I just want to skip this one. So now I'm going to do some calculations of and I'm going to show the calculation of the scattering cross-section and absorption cross-section of the gold nanoparticles. So here we kind of see that gold nanoparticles have an optimum size. That means when I go to the lab, I know the size that I'm aiming for. I should aim a size of between 10 to like 30. So 30 should be like my optimum size, so that I expect to get mostly absorption, because scattering starts to dominate when I go to like 50 nanometers. Okay. So so one of the simulation that we make is to calculate is to look at the electric field distributions, and we use methods such as finite domain time difference. Yeah. Okay. So here we notice that when you look at the electric field distribution, of course, for complicated structures, this is when we get a higher electric field distribution. Okay. So now when I go to the lab, I have to make this this type of nanoparticles, the core shells on, and gold, magnetite, and silicon. Yeah. Okay. So with the experimental results, we find that gold, the one from the absorbance spectra, we see that gold absorbs at around 500, but now we see that it gets broader, such absorb a broader spectrum when you coat it with silicon. And here we can also see that when you also put silica on this magnetic nanoparticles such as magnetite, and we also see that it gets starting to get more absorbance. Yeah. So one of the problems with magnetite is that it is really highly magnetic, and then
we've got two minutes left.
Yes. Okay. So we couldn't get a chance to look at under a microscope. So in order to work around this, to determine the size, we use two programs. We use the Langevin equations, and we also use the Rietveld refinement to estimate the size of these nanoparticles. Okay, so when you use Rietveld, you get about 8.6 nanometers. And when you use Langevin, you get about 22. But now when you want to see for the coated one, you see that the sizes increase as you see we get from 8 to 12, and here we get about 35, which shows that there's a shell. Okay. And another one was Raman spectroscopy. But now what I want to show is the final result, since I'm running out of time. So yeah, some of the results that we got the efficiency from the pristine one, which was 5.07. We got the highest efficiency with the gold nanoparticles coated with silica, and also the efficiency that from magneticals increased from 5 to 5.27. So okay, so my conclusion is that magnetic nanoparticles also exhibits effects similar to noble metals, and incorporating them in commercial devices with plasmonic nanoparticles capture photons more effectively. Then coating them also improves the magnetic nanoparticles. Okay. So now what we're trying to do is we're going to have the magnetite, and we want to coat it with gold nanoparticles instead of just having the gold nanoparticles, and all incorporate gold or silver nanoparticles inside zinc oxide, and use rare earths. Yeah. And yeah, I'd like to thank both my supervisors, Prof. Mwangi and Prof. Quant, and for funding from the Center of Excellence and the School of Physics and Chemistry and the Timber Labs to use their facilities. Yeah. Thank you.
Thank you very much for a nice presentation.